Welcome to this explainer. Today we're jumping right into grade 8 geometry, specifically exploring what we call Geometry Basics B. Think of this whole thing as your ultimate guide to assembling a mathematical geometric toolkit. Just like an architect or a builder relies on a really specific, specialized set of tools to construct a sturdy building, we're going to build, analyze, and verify geometric structures using our own connected set of mathematical tools. It's going to be a pretty fascinating journey, taking us all the way from a fundamental grid to formal logical proofs. Let's get into it.
Okay, here's our agenda for the toolkit today. We'll start with 1. The coordinate blueprint. Then 2. Distance and midpoint tools. After that, it's 3. Congruence and rigid motions. 4. Formal geometric constructions. 5. Proof, the logical inspection. And finally, 6. Our toolkit recap and transfer.
All right, starting us off, Section 1, the coordinate blueprint, laying the foundation.
So you know every great structure has to start with a perfectly measured, solid blueprint. Well, in geometry, our blueprint is the coordinate plane. And to really understand where this comes from, we actually have to look way back to the 17th century mathematician René Descartes. Now, legend has it that while he was lying sick in bed, Descartes was just staring at this fly, crawling around on his ceiling. And he realized something brilliant. He could describe the exact location of that fly just by looking at its relationship to the perpendicular lines formed by the adjacent walls of his room. And boom, that little observation gave us the Cartesian coordinate system. It's basically this two-dimensional plane where a horizontal line, our x-axis, perfectly intersects with a vertical line, the y-axis. It is literally the absolute foundation of our entire geometric toolkit.
And this system brilliantly illustrates how every single point becomes a highly specific address on our blueprint. Those two intersecting axes, they divide the entire plane up into 4 distinct quadrants. Right in the very center, exactly where those lines cross, we've got the origin, which we define mathematically as 0, 0. And from that origin, we can pinpoint any location we want using an ordered pair, x, y. The x simply tells us how far to move horizontally, and the y tells us how far to move vertically. By doing this, it's almost like magic. We can take these complex algebraic equations and turn them into clear visual graphs. It gives us a really concrete way to visualize the relationship between completely different quantities right there on our blueprint.
Moving right along to Section 2, distance and midpoint tools, the measuring tape.
Okay, so now that our blueprint is laid out on the grid, we obviously need a way to measure the materials we're going to use, right? The absolutely crucial point here is understanding the key difference between two incredibly fundamental measuring tools. So on the left, we've got the distance formula. Think of this as our literal tape measure. We use it for determining the exact length of a line segment between any two given points. And honestly, what's beautiful about this formula is that it's directly derived from the Pythagorean theorem. You know, a squared plus b squared equals c squared. It's basically just calculating the hypotenuse of a hidden right triangle sitting there on our grid. Now looking on the right, we have the midpoint formula. Instead of giving us length, this one gives us a specific location. It finds the exact dead center point between two ends, and it does it simply by averaging their x and y coordinates together. So to sum it up, one gives us length, the other gives us location.
All right, time for a pause check. Let's test our understanding here. I want you to grab your mental measuring tape. Imagine you're looking at a map plotted out on a coordinate grid. If a town called Elmhurst is sitting right at the origin, 0, 0, and another town, Franklin Park, is located at the map coordinate 8, 7, how do you find the shortest actual distance between them?
Okay, here's the immediate reasoning. Because we want the shortest straight line distance, we're going to grab the distance formula. First, we take the difference of our x coordinates, so 8 minus 0, and we square it to get 64. Then, we take the difference of our y coordinates, 7 minus 0, and square that to get 49. Add those two together, you get 113, and then just take the square root. So the shortest distance, what we always call as the crow flies, is approximately 10.63 units. And just like that, you use the Pythagorean theorem to perfectly measure a diagonal distance straight across your blueprint.
All right, let's jump to Section 3, congruence and rigid motions, building blocks.
Let's see how our toolkit handles identical building blocks. Because sure, we know how to locate points and measure them, but how on earth do we know if our building materials are exactly the same size and shape? Well, this brings us to a huge concept, congruent figures. In geometry, two figures are perfectly congruent if one can be obtained from the other entirely by rigid motion. Now, what does rigid actually mean here? It means the object acts like a solid piece of steel. As you move it around the blueprint, it completely preserves its exact distances and exact angles. No stretching, no shrinking. It stays perfectly intact.
So there are 3 main types of rigid motions we use to manipulate these building blocks.
First, we have translations, which are simply sliding an object across the plane. Then we have rotations, which just means turning the object around a central point. And finally, reflections, which is basically flipping the object so it looks like a mirror image. These rigid motions are absolutely crucial because they ensure that if we cut a triangular shape out of our blueprint, we know for a fact it'll fit perfectly somewhere else. Actually, this physical principle forms the very foundation for our standard triangle congruence criteria that you probably remember: angle, side, and side, side, side. If those specific matching parts are there, the whole rigid building block matches perfectly.
Okay, it's time for our second pause check to test your architectural knowledge on these transformations. Imagine a figure on your blueprint undergoes a translation, then a rotation, but then it undergoes a dilation, meaning it gets scaled up in size. Is the final figure congruent to the original one?
And here's the immediate reasoning. No, absolutely not. By definition, a dilation changes the physical size of the object. It literally stretches or shrinks our materials. So that makes it a similarity transformation, definitely not a rigid motion. The resultant figure would just be a scale model, a similar figure. But since the distance between the points has actually changed, we've completely broken congruence. There's no way they're congruent anymore.
Let's move right into Section 4, Formal Geometric Constructions, the Blueprints.
All right, now that we have our building blocks defined, let's look at how we formally draw these shapes out. Because when you're tasked with a geometric application, you definitely can't just guess. You need a rock-solid structural plan. So you should always follow this really reliable 6-step problem-solving strategy to keep your work mathematically sound. Step 1. Read the problem and actually draw the figure, labeling it with whatever information you're given. 2. Identify exactly what it is you are looking for. 3. Name your variables. 4. Translate all of that into an equation using the formulas from our toolkit. 5. Solve it using good, solid algebra. And 6. Always check your answer to make sure it logically makes sense within the physical constraints of the problem.
Now, when you are actually doing this physically on paper, formal geometric constructions require some very traditional tools: the compass and the straightedge. These are the classic, ancient architectural techniques for absolute perfection. Think about it. Without using any numbers at all, you can use these simple tools to perfectly copy segments, bisect angles precisely right down the middle, construct perpendicular bisectors, and even draw perfectly parallel beams. You can even build incredibly complex shapes, like equilateral triangles or regular hexagons inscribed flawlessly inside a circle. It really is the art of pure geometric drafting.
All right, on to Section 5, Proof, the logical inspection.
So, we've drawn our blueprints, we've measured our segments, and we've successfully transformed our congruent building blocks. That brings us to the final phase, the logical inspection. If you look at Mathematical Practice 3, notice how it highlights a core principle of our entire field. A mathematically proficient student absolutely must be able to construct viable arguments and critique the reasoning of others. You can't just look at two things and say, yeah, they look the same. No way. You have to build a rigorous, logical progression of statements to explicitly prove the truth of your conjectures.
You see, a mathematical proof is basically our formal building inspection. It uses literally all the previous tools we've discussed to guarantee that our geometric relationships are undeniably true. For example, we can use our knowledge of rigid motions to formally prove the Pythagorean theorem. We can write out step-by-step proofs showing that vertical angles are always congruent, or that alternate interior angles match perfectly when a transversal cuts across parallel lines. We can even prove that if you take any triangle, tear off its 3 corners, and put them together, they will inevitably form a straight line, verifying that the interior angles always sum to exactly 180 degrees. This proof process, it's exactly what makes geometry a rigorous science rather than just a guessing game. And that brings us to Section 6, Toolkit Recap and Transfer, the final inspection.
Wow, okay, we've covered a lot of ground today, so here's a concise recap of how all these concepts connect into our One Master Toolkit. We started off with the coordinate blueprint, plotting our exact x, y locations. Then we grabbed our measuring tape, using the distance and midpoint formulas to mathematically quantify that space. After that, we established our building blocks, really understanding congruence through translations, rotations, and reflections. From there, we mapped out our blueprints using formal geometric constructions and structured problem-solving steps. And finally, we performed the logical inspection by constructing formal mathematical proofs to completely guarantee our work is correct. We basically unified plotting, measuring, transforming, drawing, and proving all into one incredibly powerful toolkit.
Before we go, I want to leave you with a provocative transfer question to really test your new skills. Imagine you're an inspector on a massive, real-world engineering project. How would you use your coordinate formulas and your congruence toolkit to mathematically prove that a newly built wheelchair ramp is perfectly congruent to the original safety blueprint model?
Just think about how you could map the physical ramp onto a coordinate plane, grab that distance formula to verify the exact side lengths, and then use your rigid motion criteria to prove, without a shadow of a doubt, that the physical build matches the design safely and perfectly. That right there is the true power of geometry. Thank you so much for joining me for this explainer, and I'll catch you next time.